Good.
Okay. All right, so it's great to speak here in person and yeah, about my computational result. I mean, even though I'm having slides, but this is not actually a slides talk. This is purely because like, I don't know, if I'm doing slides, I can't get myself talking in the normal speed. So I decided to still do a writing talk. Anyway, I'm talking about computation. That's why I have slides, because, well, regarding spectral sequence, I can't draw them. And when I'm writing, so probably I'm gonna close my camera just for yourself, for you not seeing my spelling, so that's kind of awkward. Anyway, speaking too many things, okay. So this is a computational result about atom spectral sequence. So some of you might familiar with that, others probably not, but don't worry about that too much. So maybe, let's see. Can you guys see the note or is still slides?
Still slides for right now.
Probably I should. There is no option for me to share my screen, I think, so I need, okay. Anyway, so this is my note now, and maybe I should switch to writing, so. I'll leave my camera like that, or, well, maybe for internet purposes, I'll try to close that. Oh, whatever, okay. All right, so maybe the first thing, let's talk about the atom spectral sequence for a little bit. So that is a powerful computational tool, of course, developed by atoms, and it converted to some modification of the homotopy group of spheres, and that's the major concern of most of the topologies. And okay, so the E2 page of this thing is known as the X group. And of course, the E2 page converted to the E infinity page, and if we can see some pattern on E2 page, that's gonna tell us about the result they are converging to, aka the homotopy group of spheres. So we would like to develop some pattern of the E2 page. And credit to Dan Isaacson, we have this very good chat of the atom spectral sequence. Okay, so this is classical atom spectral sequence, and the x-axis is the stem, and the y-axis is the atom's filtration. And the E2 page, we can see, well, here is a red line, and above that, there's nothing. So this red line is called vanishing line. Oh, this is really annoying to switch. Okay. So we have this pattern vanishing line. And if I'm using the filtration and the stem, then this line is given by 1/2 plus 3/2. And this result is by Adams 60. Okay, and then we have the another line, and okay, so sorry, the orange line above that, we can see some repeating pattern. See this sharp angle, and it's repeating. So above this line, we have some periodicity going on, and it's called V1 periodicity, and I will come there later. So this line is also called V1 periodicity line. And above that, multiplied by this V1 thing is an isomorphism. And then this result is given by 1/5 plus 12/5. And this is the result by Adams and May shortly after that. Okay, so let's talk about this V1 periodicity for a moment. So the V1 coming from this element P, which is V1 to the 4th, and it's an element at 8,4. So if we go back to the spectral sequence, and this is okay, this is a zoomed in version, and you can see 8,4, there's nothing. So P is not actually in Ext, but multiply by P still makes sense. So because P is not an element in Ext, so that caused a problem. How do we actually define this V1 periodicity? Okay, so that is defined by another map called messy product. So messy product is a bracket thing, and it can be defined more general, but the case I'm majorly talking about is, let's denote PR, where R is actually a number, PR blank to be HR plus 1 and H0 2 to the R and then blank. Okay, what are those HR and H0? Well, here is something I have pre-drawn before this talk. So if we consider the classical dual standard algebra, we know we can think about the generators, those CIs, and okay, so I'm drawing those circles to indicate they generate the sub-dual standard algebra, A1 dual, A0 dual, so this little check is indicating dual. And then I'm also writing their corresponding main names here. So you can see that C1 is corresponding to H0. By the way, H0 is actually H10. Also H1 is H11. So their corresponding main name, and well, I like this picture a lot. And so here I'm using main name. Okay, I haven't told you how the bracket is defined. So how this is doing, if I plug in an Ext, if I plug in an X to this bracket, then it is defined by, so if I'm having a C times X plus HR plus 1 times Y, where, okay, I want the differential of my C hitting the product of the previous two position in my bracket. So the differential on C is HR plus 1 times H0 2 to the R, and I want the differential on Y is hitting the product of the later two position. So H0 2 to the R times X. So this is how the bracket defined. And okay, so if I'm consider P sub 2, okay, 2. Then this will be H3, comma, H 0 to the 4th, and then blanket. Okay, and then, well, we know that this P, which is V1 to the 4th, if I'm writing it in the main name, it will be H2 0 to the 4th, and we have a D2 differential on P hitting H3, H0 to the 4th. So that gives us this P2 I'm keeping writing R. Okay. P2 of X is P times X plus HR plus 1 times something. Okay. Okay, questions so far? All right, so you can see this messy product is not actually defined on Ext. It is defined from the kernel of the middle thing, and then landing to the co-kernel of HR plus 1. So those things in the co-kernel that is affecting it to be well-defined is called indeterminacy, and it's some work. We need to check that it has 0 indeterminacy and such. But messy product is the way we are describing this V1 periodicity. All right, so this is the story for classical, and let's come to the motivic. And well, it's okay. Well, I don't know why it's zoomed in. Okay. So if we talk about the motivic case, and throughout the talk, it will be only consider the complex-motivic. Then, well, the motivic stable homotopy category is introduced by Vygotsky as 0.3, and I'm not going to step into that. So briefly speaking, there is a stable homotopy category, and the spheres become bigraded. That's kind of important. And then from there, we still have a motivic atom spectral sequence. And this is developed by Dahlgren and Isaacson. So, well, the spheres are two-dimensional now, so the spectral sequence becomes three-dimensional, as you can expect. And of course, we're looking into the pattern. So this is going to slow strong. Alright, so we have three-dimensional now, and the stem and the titration kind of stay the same, but the motivic light is coming out.
I think your audio is either echoing a lot or not coming through clearly.
Okay, so let me try to stop sharing and switch my stop radios and just get better.
Is where your microphone is the same as before?
Yes.
The audio is just not very clear for some reason.
Try to increase the volume still a problem. Am I speaking clearly?
There's either still a lot of background noise or something. I'm not sure. Maybe try speaking again.
Okay, so I'm not sure. I think that is kind of quiet. So,
Leaving the meeting and coming back and see if that fixes the audio issues.
So let me try that.
Hello.
Okay, so.
We can hear you again.
Okay, great. For a moment, I thought I'm not coming back.
Yeah. Glad you made it. Okay, you should be able to share again and we can now hear you. So hopefully this will work.
Oh, technology.
Yeah.
All right, so now let's share, and this is not what I want you to look at. Okay, great. So now you see the Motivic atom spectral sequence. It's three-dimensional. And so the extra dimension we are adding is the Motivic weight, and it's coming outside. But actually, if you're familiar with the coefficient, that is the homology of a point, then you know what is tau. It is actually have Motivic weight negative, so it's pointing inside. All right, so the E2 page, namely the Ext, there's still pattern, and we can see those, well, if we zoom in a little bit, we can see, okay, so the difference. So before classical, we know that this slope 1 thing, H1, it stops at here at 3,3, so it's torsion. Compared to that, H0, that there is a small arrow, so it's a tower is going forever. So the major difference in the C-Motivic case is, well, it is no longer a torsion. So it's going forever, but the red color indicating it is tau torsion, namely there's nothing inside this paper, but it is still going forever. It is not torsion. Okay, so this thing is making our vanishing condition to be higher than classical because of course you can't have things lower than slope 1. All right, so the E2 page, we have a vanishing line. Well, this is not literally correct because, well, it's three-dimensional, so it doesn't make sense to talk about line. That's actually a plane, but it is drawn in two-dimensional, so I think, well, at least in this talk, I'm gonna stay with this language. If you go to my paper or the title even, it's called the region, so that's more rigorous. But lines are like easy to understand, right? Okay, so this is a vanishing line, and this result is by my advisor, Gu and Isaacson. Okay, I don't know how to spell his name now. 15, 15. All right, so now you know what I'm gonna talk about. I am trying to get a V1 periodicity line. All right, so before I'm jumping into that, let's coming back to this main name correspondence. So you can still have, well, you can still talk about the C-Motivic dual standard algebra, and the corresponding generator is like you add a line to this classical. So maybe I should introduce the coefficient thing here. So the cohomology, also the homology of a point classical is F2. And motivically, maybe I'm adding some C here. It will be a thing called M2. And this is isomorphic to F2 adjoint tau. So it's a polynomial ring. And then, well, those tau zeros and C's, there is a relation that Ci, tau Ci is the same as, I think I want a +1 here, is the same as tau I square in the dual Motivic standard algebra. All right, so there's relation between that, but the main name correspondence, you just add those one line to classical. All right, so this is the goal to attack, and how do we attack that? So let's talk about how do other people attack in classical case. So this result is basically done by Adams and May in classical case, but Ashim Krauze wrote that in his thesis. So I'm talking about what in his thesis. And maybe this is also not quite right to say his approach. Okay. And then I also need to tell you guys my notation. So I'm using this bracket and then putting the standard algebra as superscript as Ext over A, the cohomology of X, the cohomology of Y. And yeah, I know some of you might hate this notation, and I am not convinced this is the best notation also, but this is the notation Ashim is using, so I'm trying to stay consistent. And by duality, you can also think about over the dual standard algebra, which is what I was sticking at in this paper, and then you switch things to homology and dual. Okay, so an example will be if I'm putting spheres here and then put the standard algebra, I'm getting Ext. Okay. All right, so this is the first notation, and the second thing I would like to list is the cofiber sequence. So if I have a map between sphere spectrum, let's call it alpha, and then I can take the cofiber and denote that as S/alpha. And then now I'm consider the self-map between this cofiber S/alpha and consider this map beta. And then I'm also gonna take the cofiber, then I'm denoting that as alpha comma beta. And this thing is actually, it have a name called the generalized Smith-Toda complex. but it's just a iterated cofiber. Plus some condition, but don't worry about that for now. All right, so that's a cofiber, and it will become clear why I'm trying to consider that later. And also, I would like to consider the fiber sequence for a reason. Okay, so how do I consider fiber if I'm inverting H0 in my sphere spectrum and then take the fiber of that? So remember, we are in a stable category, so cofiber and fiber all induce the long exact sequence in Ext. And then that is gonna bring me, okay, where is that? There we go. And then here I am having S comma F0. Okay, why do I want to do that? That is because I want to make the vanishing line to actually saying the correct thing. Remember, we have that H0 tower at the 0 stem. So that is certainly above the vanishing line. So to say the vanishing line like that is not literally correct. So if I'm drawing some picture here, so the Ext will kind of be like this, where you have this H0 tower and you have some pattern like this, something like that. And then now you are inverting the only H0 tower. So now it becomes double-sided and the rest stays the same. And this cofiber part, sorry, I'm saying cofiber. This fiber part is more like taking the complement. I mean, it's more complicated than that, but for now, it's enough to think like that. So the torsion part stays the same, and then you have a shifted negative tower, but the positive tower goes away. So talking about vanishing line here actually is correct. So I think for now, I'm gonna replace everything with this thing to talk about vanishing condition. And this is why we are considered this fiber sequence. Okay, so enough for notation. And let's see how Crozy is attacking that. So what we want, the goal is to show a map on Ext. Well, I'm repeating that with F0. This P sub 2 to show this map when this map is an isomorphism. And then, well, P is not in Ext, and let's briefly write in this. And it's not also not an element in S comma F0. But P is in the cofiber of H0. So what's the benefit? We can talk about multiplication by P in here. So let's put it in our diagram. And the vertical map is exactly induced by the cofiber. So now I can put blank multiply by P here. All right, and now, so P can be considered as self-map on S mod H0, so I can extend this thing to make it a long exact sequence. questions so far? Okay, so this is a commutative diagram, and we want to know when this P2 thing is an isomorphism. So how do we show that? Well, first we need to worry about when the multiparticle is defined and the zero indeterminacy, but that's not what I'm going to talk about briefly today. And then we also need to worry a little bit about and then, okay, sorry. I think I'm bad at writing and saying things at the same time. So when that is an isomorphism depends on when the vertical maps are isomorphic. And this is also not the point I'm going to concentrate today. Okay, so now you can see we get this edge, the vertical edge, this edge and that edge. And then I want to get this edge also. And when this multiplied by P is an isomorphism depends on the vanishing condition here, which is the same as here. Maybe I should add some suspension, a shift, but briefly speaking, it depends on the vanishing result there. And this is what I would like to talk about today. So if I get the vanishing condition here, then I know when multiplied by P is an isomorphism, plus when the vertical maps are isomorphism, then I get the fourth edge of this square. So that's the result we want. And Ashim Krause did he compute the vanishing condition on this group and then deducts the result. Okay, so what's the difference in Motivic case? So as we see before, the vanishing condition is different. And well, we see this approach that the periodicity result is actually rely on the vanishing condition somehow. So that's bad, right? And why the vanishing condition are different? Because there are H1 towers. And those are the things we don't want because it is making the vanishing condition higher. So that is preventing us to get the same result classically. So we want to throw it away. Well, this is the idea, but mathematically, how? And then that is to say we need to consider another fiber sequence. Because we have used that to throw away the H0 tower, and we can also consider using that to throw away H1 tower. So now let's consider inverting H1 on F naught. And then taking its fiber to be F01. So you can image that this thing will have no H0 and H1 tower. Maybe I should use or. Sorry, forgive me about my English. Well, it will have sort of negative towers, but not positive ones. And then because for the computational convenience sake, this thing can also be expressed as a colimit and with some shift. And the colimit, I'm denoting that as this, H1 infinity, because it is the colimit of multiplying by H1. So in the middle, you will get shifting I and H1 to the I. All right, so this is for computational purpose. And okay, so what's the idea? The idea is I'm gonna throw away all the H1 towers, so replacing the classical F0 with now F01, or more like this colimit for our computational purpose. Okay, so I'm gonna take advantage of myself. This is the only thing I like about technique. All right. Right, so if I don't have the superscript, I mean it's over the dual standard algebra. And I probably forget to write the dual before, sorry about that. And well, that is too large. I mean, it's hard. So we can start with something small. Such as, well, the sub-dual standard algebra A of 1. And that is something I can do, and I'm gonna show you some picture. Okay, so this is before we multiply, we taking the generalized Smith to the complex. You see P is not there, and I probably use theta instead of P in this slice, and it's not taking the colimit yet. So a starting point, and then if I'm taking the colimit, namely taking the fiber, then I'm getting those shifted negative towers. And then because multiply by P is still injective, so taking this iterated cofiber, I'm only getting one pattern as sort of the complement. Okay, so remember this pattern. This is our starting point. We are starting with a smaller thing, A of 1 dual, and this is the starting result. So the thing we want to remember is the vanishing condition here. Well, nice and clean, and two-dimensionally, we can think of the starting vanishing condition is flat. Well, f greater than 0. Great. Okay, so how do we move from A1 dual to A dual? That's a huge gap, right? Well, we need another computational tool, and that's called Cartan-Ehrenberg spectral sequence. And I believe the date is 99. Okay, so how that works, that is, if you have an extension of half algebra, providedly prefer simple, no, not simple, normal, that's the word, extension. Let's say E mapping into gamma, mapping into C, and that's a normal extension. And if you further have the collection of E on gamma to be free, then you can get a nice splitting of your E2 page to be okay, X over E of your coefficient tensor X over C, what you want to compute, let's use M and N for now, then convergent to X over gamma. So side convergent to what's in the middle. All right, so switching to our notation, this is sort of like M n bracket over C, and well, I'm talking about our case later. Sorry about that. Okay, this is how the spectral sequence work, and let's see what extension we have. Well, let's first note to move from A1 to A. Let's stop by A of 2 dual. So A2 is not different from A1.
Are we supposed to see you writing right now?
Oh, sorry. Okay, great. So hopefully when I'm writing E2 page, there's, okay, sorry about that. Okay, where I am. Yes, so the A2 dual is not differ from A1 dual by a lot. It's only some generators with some notation. So this is A1 dual. You can see it's a quotient of A2. And then, well, this is not one simple extension. It is 3 normal extension combined together, and this part is exterior. Okay, so we have 3 extension, 1, 2, 3. Okay, so now let's look at the first one. Because this part is exterior, so X over that becomes polynomial on the generator. So in our case, the Cartan-Ehrenberg spectral sequence is actually M comma N over C polynomial over this generator. Let's call the generator to be beta. and then convergent to the thing we want. Okay, so that is to say the vanishing condition on this Mn over C plus some thing about beta is gonna give me the vanishing condition on this M, N over gamma. And that is a famous lemma in my paper. Well, not actually, but yeah, that's a lemma in my paper and how that is affecting. All right, so if my M, N over C already have some vanishing condition and the beta is not higher than that. So let's just say if slope of beta on original thing, or if it is higher, but beta is nilpotent. Namely, I mean, beta is poking out the vanishing line, but it ends finitely step. So you can think of that as moving up your vanishing plane and to block them away again. So we say this, the resulting vanishing condition has parallel slope. Because it's nilpotent, you can always move it up. And then if it's other case, namely beta is not nilpotent and it's also poking out the original vanishing condition, then we need to make some modification about the slope. Well, an easy thing is you can choose the slope of beta. Okay. So let's see what are the things, the betas we are throwing in. Okay, so this is the extension. Okay, so those are the betas we are throwing in, and I think I can draw here, yes. So the slope, we are just smashing it to the screen, so we are looking at the slope that is 1/6, 1/5, and 1/3. Okay. Oops. How do I stop drawing? Okay. And then we throw them repeatedly. And okay, so the first two are the bad case. And remember, we start with f greater than 0, so the flat plane. And so tau 2 bring it up to 1/6, and then C2 bring it to 1/5. But the third one, this one is nilpotent. So we stop at 1/5. So the conclusion is, well, over A2 dual, this thing has vanishing line of slope 1/5. And then we figure out the intercept by, you can think of that as plug-in points in calculus like that. Yeah, we figure out the intercept by plug-in points. So we actually get the vanishing condition here. Okay, so you may ask, well, that's over A2 dual, it's not A. Okay, well, so moving from A2 to A, you throw a lot of things, basically infinitely many generators, but they all have slope lower than 1/5, so it's not gonna affecting the result. They're all already below our vanishing plane. Okay, so that's easy. We move a large step and it's kind of for granted. And then let's return to our diagram here. And I'm listing the vertical maps are isomorphism when that. And this coincides with when the Massey product indeterminacy is vanishing also. And then, yeah, so the vanishing condition is that. And plus, combine those together, we get when this PR, when is my pen? When this thing is an isomorphism as the first edge. Okay, so do I get actually a V1 periodicity line? Well, not quite, because remember we have thrown away all those H1 towers, so we can't get a full result. So we need to add some modifications. So this yellow line stays the same with classical, except those H1 towers. And this is the result. Okay, so let me briefly say 2 minutes about those H1 towers also. We have some control on that because there are H1 inverted Motivic Ext studied also by my Weiser, Gill, and Isaacson. So they described all the positions of the H1 towers in that paper, but the position is described using the line because it's H1 inverted. Well, actually, in this Motivic Ext, those H1 towers are rays, not lines. So the actual starting point of those rays are not quite known for now. And I think Isaacson has a student named, well, I don't know if I'm saying his name right, it's Hugh Tai. I think he is doing something related to that. So hopefully if we know the starting point of those rays, we're gonna get a full result of when V1 periodicity is an isomorphism. All right, so that's all I have for today. And by the way, this I just got some favorable comments on this paper, so hopefully it's gonna come out very soon. And thanks for listening.
On behalf of everyone, thanks, An. Are there any questions?